All right, so today I want to talk about intramolecular forces. Now, these are the forces that hold a molecule together. So let's calibrate ourselves here. We have about 118 elements on the periodic table. That's pretty much what we've figured out. A lot of them are synthetic. I mean, they were kind of created in the laboratory, a lot of those heavier elements. But if you look at a modern periodic table, it probably has 118 elements on it. Now, those elements, you can have atoms of those elements, right? So we have atoms of elements. And those atoms of those elements can come together to form a lot more than 118 things. If the world only had 118 things in it, it would kind of be pretty boring. So you can have pure elements, but then you can also have compounds and molecules. You pretty much have the situation where they're coming together in different ways and they're bonding. So that's the bond we're talking about when we say intramolecular forces. And so there's different kinds of these intramolecular forces. We're going to get into those in a second. But here, we're pretty much talking about atoms of elements coming together to make millions of different molecules. So some of these molecules you've probably heard of, like caffeine, testosterone, water, carbon dioxide, all sorts of different molecules, substances can be created just by atoms of elements coming together in different ways and bonding. And so just to make sure you understand what we're talking about, we're not talking about intermolecular forces here. Those would be the forces between molecules. And so let's give you a quick illustration. If you had the United States, the USA, and you had China, if we were talking about international trade, then that would be the trade between nations, between countries. But if we're talking about if we were talking about intranational trade, that would be the trade that's happening within the United States. Right? So that's what intra and inter mean. So we are not talking about intermolecular forces, which are the forces between two different molecules. We're going to focus today on intramolecular forces, which are the forces that hold together a molecule in the first place. Okay, now this all boils down to the attraction. Everything here, all of these forces boils down to the attraction between a positive and a negative charge. And so we could use positive as red and negative as blue, and we have attraction between these two things. And so positive and negatives attract. You've probably heard of opposites attract. And so you're going to see that no matter what kind of bonding you're talking about. If we're talking about an attraction, it probably is coming from a positive and a negative attracting. And so keep that in mind. Now there's repulsion that's happening too, because anytime you get two positives and two negatives together, you have repulsion. But we are mainly talking about attraction. All right, now that that's out of the way, what is the first type of bond we're going to talk about? Let's talk about an ionic bond. So an ionic bond is usually a bond that happens between a metal and a non-metal. Right? Most of the periodic table is metals, but there are non-metals as well. And when you have a metal and a non-metal getting together, a lot of times it's going to come together in an ionic fashion. And so what that means is that you have a bond between two ions, which are charged atoms. We got to dive into what this actually is talking about. Let's look at an example like sodium chloride, which is table salt. All right, so if we look at that, we have a sodium atom, Na, and we have a chlorine atom, neutral. Let's say they're neutral coming together. And after it becomes an ion, we could call it a chloride ion, which is why we call it sodium chloride and not sodium chlorine usually. Don't worry about that though. Let's focus on how the bond is actually taking place. All right, so we look at the sodium and we say, how many electrons are there? Because electrons are really where the bond is taking place. Electrons are responsible for this bond for the most part. We want to keep track of the electrons. If we can understand what's going on with the electrons, we can usually understand what's happening with the attraction. And so we look at the sodium and we know that on the periodic table, sodium's number 11. And so it has protons equal to 11. So its nucleus, which is at the center, which we know has protons and neutrons. Based on the isotope, it might have different numbers of neutrons, and that's why we have an average atomic mass over all of the isotopes of a given element. And so it doesn't really matter how many neutrons there are, because I don't really care about the isotope, and I also don't even really care about the protons. Other than that, it does define the element that you're talking about. But we do know it has 11 positive things in the nucleus, right? And so it's going to have 11 negative things surrounding it, the electrons, and if it's neutral, right? And so we're assuming that there's no overall charge, and so plus 11 minus 11, you get 0. And overall, you have 0 charge. So we don't really care about the neutrons. Now, the other thing that we have to understand is that not all of these electrons we care about. So we don't really care about the protons anymore. We don't really care about the neutrons. We only care about the electrons, and of the electrons that we care about, we mainly care about the electrons on the outside, the ones that are in the highest energy levels. Those are the ones that are going to be bonding. And so we look and we see that there's 2 electrons in the first energy level. The first energy level can only hold 2 electrons. There's only 1 orbital on that first energy level. It is the 1s orbital. And so if you say 1s2, that means there's 2 electrons in the energy level 1s orbital. All right? Each orbital can hold 2 electrons. And so now we have 8 electrons in the second energy level. And so we would look at this being 2s2. There's 2 electrons in the 2s orbital. But there's also 6 electrons in the 2p orbitals, because there's actually 3 different 2p orbitals. There's the 2px, 2py, 2pz, which come together to be 6. And so notice how you add those 2 up to be 8. And so overall, in energy level 2, there are 8. And there are only 2 in the first energy level. And now the last one would be 3. We move up to energy level 3, which is the highest energy level in this atom. And so we are going to look at 3s1. So there's 1 more. And so you add those up and you get 2 plus 8 is 10, plus that additional 1, which is in this outer energy level here, this highest energy level orbital. That is going to be the electron that we care about. All right. So all that's to say that we're going to be drawing 1 dot. And this is called a Lewis dot diagram, or an electron dot diagram. We only care about the electron that, pretty much the valence electrons, the electrons in the highest energy level. All right, so now we're moving on to chlorine. Now I'm going to go a little bit quicker. For chlorine, you have, on the periodic table, you can look at the number, it's number 17. That means it has 17 protons. And if it's neutral, which if it's an atom, usually we assume it's neutral unless we're calling it an ion, in which it's not. I don't care about the isotope. Negative electrons here. We have 17, all right? We must have 17 electrons, and we're going to look at 2 of them being in the first energy level. We're going to look at 8 of them being in the second energy level, and in this case, we need 7 more in that third energy level. And it's a very similar argument to the orbitals. I'm going to kind of leave that to you guys. I just wanted to mention that. So, bottom line is, I've hopefully convinced you that there's 1 dot that I draw for sodium, and there's 7 dots that I draw for chlorine. So I'm going to do 1, 2, 3, 4, 5, 6, 7. And now I can kind of see what's happening. There's one other thing we have to understand. Because of these energy levels and how they're set up, it turns out that they really are more stable when they have a full energy level. And that kind of makes sense. And so if it's a partially filled energy, they really don't like it, and it's kind of called the Octet Rule. It tends to gravitate towards the number 8, which is like an octagon is a polygon with 8 sides. And so we're going to use that rule to try to describe this. Is it easier for sodium to lose 1 electron or gain 7? Well, looks like it'd be a lot easier for sodium to lose 1 electron. So the sodium is going to lose its electron over here to the chlorine, and the chlorine is going to gain that electron. The chlorine would love to have 1 more because it has 7, it wants to get to 8. And so we would say that the oxidation number would be -1 In other words, the charge of the chloride ion, once it's created, is going to be -1 because it just gained a negative charge. And the oxidation number here is going to be +1 because it just lost a negative charge, meaning it's now +1. And so now you have an attraction between a positive, so this whole thing is positive here, and this whole thing is negative, right? And so we have an attraction between a positively charged ion, which is called a cation, and a negatively charged ion, which is called an anion. All right? And so that attraction is what an ionic bond is. And so the reason why we're learning about these bonds is we can start to describe different properties now of these materials based on their bonds. So for example, we know ionic bonds tend to have a crystal structure, which can be classified as cubic or something like that, or orthorhombic. We also know, other than the crystal structure, it comes together to form a crystal. We also know that ionic compounds tend to have high melting and high boiling points. So they tend to be solids at room temperature, and they tend to be pretty hard to melt if you put them over a flame. We also know with ionic compounds, they're not really too good at conducting electricity when they're in their solid form, but they are able to be dissolved in water, and when they are dissolved in water in their aqueous form, they can conduct electricity, which is pretty awesome. And so we know different things about this ionic bond. We also know that a metal in an ionic compound, if you put it over a flame, you can do the flame test, and the electrons in the metal are going to be excited, and when those electrons are going to, from a relaxed state to an excited state up here, they are unstable. Okay, let's say we're at the spa and we're at the party, all right, and when they come back down, they are relaxing, and this would be excited. They're excited. Okay, so when they relax, they're going to release that energy in the form of light, and that's pretty much why we can do the flame test. In other words, different metal ions are going to glow different color. They're going to change a flame a different color. So sodium, for example, would be yellow, calcium would be orange, lithium would be red, copper is a green. So you have different colors. I think potassium is violet. So you have different colors of the metal ions in this ionic compound if you put it above a flame. So we can start to explain properties of these substances based on this bond. That is key. Alrighty, so now we go on to the next bond. Alright, this is in detail today. So covalent. So we have a covalent bond. Covalent bonds tend to happen between nonmetals and other nonmetals. All right. So if you have a nonmetal and another nonmetal coming together, it tends to form a covalent bond. And so let's give you an example of that. So we can't deal with the metal from earlier, but let's deal with the chlorine. All right. So let's draw the chlorine. Let's actually draw it twice. And so we have chlorine. We got 1, 2, 3, 4, 5, 6, 7. I'm going to draw it twice. I'm going to draw it down here. Chlorine, 1, 2, 3, 4, 5, 6, 7. I'm going to draw a hydrogen here, which is a nonmetal. Even though it sits above the alkali metals, it's still a nonmetal. It's still considered a nonmetal. And so we got these two nonmetals. Hydrogen's an interesting one. It's pretty much just a proton. And so you got, instead of hydrogen, we're just going to actually see what would happen with another chlorine. So chlorine and a chlorine could come together, right? All right. And so what ends up happening here is a little bit different than what happens over here with an ionic bond. And the main thing, the main reason for that, we like to say, is the electronegativity differences. And so if you look up for sodium, the electronegativity is 0.93. That's just a number that represents how much it wants the electron, right? And chlorine is much higher than that. So chlorine is 3.16, approximately. And so if we look at the difference between these two numbers, we have a pretty significant difference here. The difference is greater than 1.7. It's actually 2.23. So 2.23 right here, which is greater than 1.7. And so anything greater than 1.7 in terms of how different they are, we tend to say is an ionic bond. So the electronegativity difference is greater than 1.7. Okay? Over here, the electronegativity differences are not so great. All right, so metals and nonmetals tend to be pretty different. Metals tend to donate their electrons to nonmetals. Over here is a little different. And so now we have electronegativities, which we can look up. We got 2.2 for hydrogen. We already know 3.16, 3.16. And so the difference here is actually just 0, right? Because they're the same exact element. The difference here is not going to be as great as the ionic bond, but it is going to be 0.96. Okay? And anytime you have an electronegativity difference, which is greater than 0.4 approximately, but we also, so we actually can do this like this, 0.4 over here. So it's greater than 0.4, but it also, remember, has got to be less than 1.7. Somewhere in between that region is where we classify a covalent bond. And then down here, pretty much if you have an electronegativity difference that is less than 0.4. Now this is a spectrum, okay? It's not black and white. It's a spectrum of ionic character. You can see here that as the difference in electronegativity gets greater, we have more of a likelihood for that electron to be completely transferred from one atom to another. Bottom line is, if you have a pretty low electronegativity difference, it's a tug-of-war match between those electrons, then one atom doesn't really want it a lot more than another, so they're going to have equal sharing. So we can say that there's equal sharing happening here. And we'll kind of put a line there. And up here, we would have unequal sharing. We'll talk more about what that means in a second. We'll show you. But unequal sharing is going to be called polar, and equal sharing is going to be called non-polar. Okay, so let's talk about what that means. Well, with the polar, it means that these guys, the chlorine wants one more. Hydrogen would love to have a full second energy level. So hydrogen is going to want to get one more as well. So they're actually going to share these electrons right there. That is a single covalent bond. You can actually draw it as a line, which you'll see if you look it up online. Anytime you see like a line between two atoms, it's most likely a covalent bond. You can also have a double and a triple covalent bond. But a bond or a line represents two electrons that are being shared. And so if you look at it, we can count 1, 2, 3, 4, 5, 6, 7, but it actually has 8, so that's happy. And then we count here, 1, 2, that's happy. So both atoms are happy, and in the process, they don't really become fully charged like we saw before when we had a transfer of an electron. So this is a transfer of an electron over here. Here we're just kind of sharing. However, if we have unequal sharing, you are going to have something called a dipole moment, a permanent dipole moment with something that's polar. And so we use a symbol like this, dipole, meaning two poles. Like if you're bipolar, you have two poles to your mood, manic and depressant, let's say. Or we have the North Pole and the South Pole. Here we're talking about a charge separation. And so on this side, we have our positive side of the molecule. We actually use a symbol delta, like a partial positive, so like a little Greek letter there. And on this side, we have not a full, but a partial negative on this side of the molecule. And so it is it does have a little bit of unequal charge distribution. The electrons are pulled a little bit closer to the chlorine because the chlorine has a higher electronegativity. And so that's why we call it polar. Down here, they're going to share pretty much equally. And so we don't really have charge being separated. They're pulling equally. The tug-of-war match kind of cancels itself out. And so you're left with a non-polar covalent bond. And so this really summarizes the two main types of covalent bonds, but remember it's a spectrum going from 0 electronegativity difference all the way up to, you know, above 1.7. And so the higher the electronegativity difference, the more one atom is going to win over the other atom in that tug-of-war match. Where's the attraction happening, though? Well, if you remember, these nuclei, the nucleus of an atom that has the protons and the neutrons. Neutrons are neutral, protons are positive. The positive nucleus of and I didn't actually draw it, we're being a little bit lazy here. That's okay. But there's an invisible positive nucleus to each of those atoms, right? And that positive nucleus is going to be attracted to that negative region of shared electrons. And so that shared electron region, which is negative, is going to be attracted to this positive, but also that positive. And so they're both attracted to the same region, and they're being held together by a covalent bond. And so that's where we get our positive attract negative idea from. So the other thing to mention is that these other electrons that are not participating in the bond, those are called the non-bonding electrons or the lone pair electrons. That's just a little bit of vocab for you. Okay, one more little illustration for you. Nitrogen and oxygen. For oxygen, you actually have a double bond. Okay, and so for oxygen, you have 1, 2, 3, 4, 5, 6, and then same thing on this side. 1, 2, 3, 4, 5, 6. Let's do it like this. And so notice how pretty much this is sharing and this is sharing, so you have a double bond between the oxygen. And the nitrogen is actually going to be a triple bond. I'm going to be lazy here, draw it like this. But you got 1, 2, 3, 4, 5, 6 electrons represented by those lines. You need 2 more on either side. All right? And so here we had 1, 2, 3, 4, 5, 6, 7, 8, right? Everything's happy. Bottom line is that these are called diatomic molecules. This is the majority of the air. So about 80% of the air is nitrogen, but the rest of the 20% is pretty much oxygen. Obviously, there's other stuff too, like water vapor and carbon dioxide. But the key idea here, guys, is that covalent bonds are another type of bond that we learned about, and they have lower melting and boiling points. You can think about this. Oxygen and nitrogen, which are the majority of the air, they're already gases at room temperature. You can also think about something like HCl, hydrogen chloride gas, or even if you put it into water, it's hydrochloric acid. Water itself is something that is a liquid at room temperature, so it's already melted. And so think about these covalent bonds as a little bit easier to break. It doesn't take as much thermal energy to break these bonds. When you heat them up, they melt a little bit easier. They tend to, at least. These are general rules. They're not as good at conducting electricity. Now you do have the two different types, though. You got the polar and the non-polar. So when we're dealing with polar, we have a little bit of charge separation going on. But definitely when you get to these non-polar ones, not as much charge separation. And so the last type of bond we're going to talk about is the metallic bond. And a metallic bond is between a metal plus another metal. All right, so we got the last combination there, a metal and a non-metal. We got non-metal, non-metal, and now we have a metallic bond, a metal and a metal. And so this one is pretty interesting. Let's say that we have sodium. We could do sodium. Now in this case, we're talking about solid sodium metal. So you have Na, Na, and we can just draw a bunch of these Nas actually if we want. Usually we do. You can do the same thing with copper or any other metal. So usually when metals get together and bond, this is how it happens. So you got 1 electron to donate here, it looks like, from what we said before. And so let's just assume that each sodium donates 1 electron. and if it donates that electron to the pool, so let's say that there's a shared pool in the middle here, for simplicity. When that electron leaves, all of these sodium ions are going to be left behind, these cations. So you have this structure, this lattice of positive charges, and then you got those negative charges from the electrons. And so we end up with an attraction between the metals, the positive cations, and the electrons that are kind of free to move about. They're like mobile electrons. It's like a sea of electrons. And so the attraction between this pool of negative charge that is kind of flowing, you can think of, and the positive ions that are left behind, that would be a metallic bond. And so these are bonds that really explain why metals are good conductors of heat and electricity. So for example, when you hook this up to a battery, so let's hook it up to a battery. Let's pretend that this was like a wire. You could pretend like that's copper too if you want, because copper is a lot of times what we use for wires. Now let's say that we have a negative terminal down here for let's say a battery, and let's say we have a positive terminal up here. So this positive terminal of the battery is going to be pulling the electrons towards it, and then the negative terminal is going to be pushing it away, and so we can have like a net flow of electrons and electricity through that material. So it's pretty good at conducting heat and electricity. It also is pretty good if you hammer it. It's pretty easy at bending. It's malleable. It is ductile, so you can stretch it into a thin wire. And so a lot of the properties of metals are explained by this illustration right here of metallic bonding. And so yet again, we have an attraction between a positive and a negative region. And the other thing to point out is that not all metals are the same, and so certain metals are going to share electrons to the pool a little bit better. And so certain metals like gallium and mercury that don't have high melting and boiling points, they are actually pretty much liquids at room temperature, at least mercury is, and it's very easy to melt gallium. They are not very good at sharing their electrons, and so they're really not going to have as much attraction, and so when you heat it up, it'll be easier to break those bonds and turn it into a liquid. So we can look at these models, and that's really all they are, is 3 different models that we have of the different types of bonds that can happen between atoms. And when we look at this, we can start to describe the properties of all the stuff around us, all the matter around us. And so that's really the point.
And so here's a summary before we get to the real life stuff of these 3 types of intramolecular forces. You got the ionic bonding, the covalent bonding, and the metallic bonding. The ionic bonding is between a metal and a nonmetal. The covalent bonding is between a nonmetal and a nonmetal. Metallic bonding is between a metal and a metal. Notice how the metallic bonding is kind of like a combination of the two, because you still have the ions, but you have like this ultimate form of sharing.
All right, let's show you some of these properties here. So here I have a 9-volt battery, and based on the multimeter measuring voltage, we have 7.4 approximately volts being produced by this battery. It's not quite the 9 volts that it says, but that's because it's a little old. And so if I take this battery and I hook it up together, and so let's unhook it from these leads here, and so I have just little paper clips. Now you'll see when I touch these together, it creates a circuit, and now you have the light is lighting. So the wires go in there, and there's a little resistor, but for the most part, that is just electricity going right through that LED and creating light. So we're going to use this to test the conductivity of these different materials. And so let's start off with a little bit of tap water. So this is water from the tap, and so I put it into here, so pretty much coming right out of your faucet. We're going to see if electricity can be transported from point A to point B using this test here. And so let's
we'll have one side in this water over here, and we'll have the other side. We'll touch that water and we'll watch this light. You can see a little bit there, so it's definitely got something in there. All right, so I have it's transporting. You can see how that's lighting up. It's transporting electricity through this water here, but there's definitely something in there. So like tap water already has stuff dissolved in it. Okay, now let's try the same type of thing, and we'll see if it works with just purified water. So this is water that has been purified. We'll see if it's better or worse at conducting electricity. And so we'll do the same thing, and we'll put one all the way over here, and we will put, I'll just set it all the way in there, and then I'll just touch it about the same distance as the other one, and we'll see if we can see it light up. So the one end sitting in there like before, and not really anything. If I get really close, so I wonder if it does it. A little bit. So you can see if I get really close, it does it, but if I'm far away like I was before, not really much. So purified water, if it's pretty much perfectly pure, it's really not good at conducting electricity, but we know that tap water that already has stuff dissolved in it is. And so some of the stuff that you can dissolve in that water is this stuff. And so let's do a quick test. So we have, here we have a covalent compound. It is salicylic acid. It's like pretty much an acne medication. It's a precursor to acetylsalicylic acid, which is aspirin. It's used as a over-the-counter medication. And then you have, this is a pretty complicated one, but notice how you have all non-metals here. So there's a bunch of covalent bonds. And notice how the positive nuclei are attracted to that shared negative electron pair. And so that even though it's a pretty complicated molecule, this is a phenyl group, which is a ring of carbons. It's pretty much like a benzene ring with something attached. And then over here, we have sodium chloride, which is NaCl. We definitely have an ionic compound, so you have that positive ion and the negative ion attracting. And then over here, we have a piece of copper, and that's pretty much going to look like this, where copper is donating a certain amount of electrons to the pool, and just like we were saying, it is going to be attracted to that shared pool of electrons. All right, so let's start over here, and let's first see how well it conducts electricity. If I pour the pure water, so I'm going to use pure water, and I'm going to wet this substance here. So I'm going to wet it down, and I'll touch the one side here, make sure the other side's touching as well. I'll touch that, and so we can kind of see it light up a little bit. Yep, see it light up just a little bit. Okay, lighting up just a little bit. It's definitely able to be transported through, but not all that good. Not compared to just actually touching the metals together, right? So if I touch it closer, it's going to be much brighter, much brighter. Okay, so now let's try the same thing with the sodium chloride, the ionic compound. And so with the ionic compound, we will wet this. Now ionic compounds are pretty good at dissolving in water, and so we'll take the one side, we'll put it in here, we'll take the other side, we'll put it right here, and we can see that that's glowing very brightly. So ionic compounds are very good at conducting electricity. You can see that these wires are pretty far apart, but the second I add some of those ions into the mix, that's glowing a lot brighter than before. And so I can take that wire out, and then I'll put it back in. Clearly, up and down. Very bright, even at a pretty far distance. Okay, so we are able to send electricity through an ionic compound if it's dissolved in water. If it's not dissolved in water, if you just had some salt and you were to have it on the table, like in a solid form, okay, you're not really going to be able to send the electricity through it, okay? So I can pretty much do this and this, and we'll touch it, and we really don't see any light happening. So it's not able to be conductive in its solid form, but once you dissolve it in water, those ions can be kind of ripped apart by that water, and we can conduct electricity. Okay, our last little bit with electricity is, last but not least, clearly you probably know what's going to happen, but just for completion, we have this side touching. Okay, we got the metallic bond. Let's pretty much set this up. So I got one side touching each, and so that side's touching that side, and I'm going to complete this circuit here. And wow, that, I mean, we got to make sure it touched, but you saw it there for a second. I try my best to get this going. Wow, that's probably the brightest. I think you would probably have to say that that's really good at conducting electricity, and I don't have to do anything to it. Like, I don't have to dissolve it in water or anything. So you can see why most of the time we use metals for conducting electricity, because they're really good at conducting electricity, and you don't have to, mess around with dissolving them in water first or anything like that. All right, so that shows you some of the electrical conductivity. Now this is gallium here, which is one of those ones that it might not be as good at conducting electricity. It's definitely weaker at bonding. It is not as good at sharing, and so it has a very, very low melting point. So let me just touch one side somewhere in there, and I'll touch the other side somewhere in there. And even still, you can see that light up. Okay, so look at that. So even this metal is pretty good at conducting electricity. So let's look at something else. So remember how I said that ionic compounds have a crystal structure. So let's look at that real quick. And so one thing that we could do is take a little bit of salt and pour it in a little bit of a petri dish here. And there we go. And now we look at the salt under the microscope, the NaCl, and this is going to magnify it quite a bit. And so we can look in here to the best of our ability. See if I can focus in on that for you. Wow. Okay, so now you see the crystals there. So look at that. I'm just adjusting the light. And so that is cubic. That's the sodium and the chlorine. Pretty much those ions are arranging themselves in a cube. And so you just have each of the sodiums are surrounded by chlorines, and each of the chlorines are surrounded by sodiums, and they form this crystal lattice structure. So pretty awesome to look at some of those under the microscope. And then we could even look at a different ionic compound if you want. We could look at something like copper sulfate, and so that's that blue chemical there. We'll put some of that in the petri dish for you. And so this right here, check this out. So this is a different crystal structure, and you can kind of see that we have different shapes happening. And let me try to move the dish a little bit. Look at that. So we have different crystal shapes for ionic compounds. It's pretty awesome. You can classify them. And then, other than just looking at the structure, we can also talk about the melting point and stuff like that. So let's start with one of the ones that I think is pretty cool. We can start with this metal here, and we said metals usually have high melting and high boiling points, but this is gallium, all right? And gallium has a very, very low melting and boiling point. So I'm just going to use a little bit of a lighter here and just get that heated up. You can already see it melting. Look at that. So it looks like mercury. Just going to heat it a little bit. All right, and so I heated that up good, and that is a liquid metal now. And so it's really not all that hot. And let me just come a little closer to it. Yeah, it's not too bad at all. Okay, so let me actually pour some of this in my hand. Okay, so we'll take this and I'll pour it into my hand. All right, it's actually pretty cold. All right, so this is cold, and it's really cold right now, even though I just heated it up. So just my body temperature will actually keep this thing a liquid. So we're actually holding a liquid metal. Now this is not mercury, so it's not as dangerous. I'm sure you've heard of mercury poisoning. This is gallium, so a little bit safer to handle and pretty cool. Now, so this kind of proves that there's exceptions to the rule, right? I mean, not all metals are very hard to melt, but when you get up to something like tungsten, that's going to be really hard to melt. So you have to kind of generalize these properties, and it all comes back to our model. And so there you go. Pour that back in there. All right, so the next thing I wanted to show you is the flame test. And so we'll turn the methane gas on to the room, and we will use a sparker to ignite, give enough activation energy to this reaction here. And methane itself is a covalent compound. It's just pretty much CH4. And so we have some methane gas combusting with the oxygen, which is another covalent substance, another diatomic covalent molecule. And so those two things react, and it's combusting, and we see that flame there is currently blue, and you can definitely see some flashes of contamination every now and then. But I wanted to show you that, remember, different substances like salt is going to have a different flame color. And we're back to ionic compounds. And so ionic compounds, if I take a little bit of this table salt right here, so let's take some of this. That should be enough. Now if I take this table salt and I put it in the flame, I know that sodium is yellow, and so it should give me a yellow color. Yep, so I got that nice yellow color. That's awesome. All right, so now I'm going to rinse this off. And so we don't want any contamination between this one and the next one, just to show you. Now I'm going to show you this too. If I heat this up, it's really not, it should not be changing the flame color. There we go. Okay, so it's not really changing the flame color at all, like this metal, the spatula. Now let me show you this blue copper sulfate. It's another ionic compound. This one's green. I don't know if you saw that. That's pretty awesome. We got green now. And also notice that as it heats up, it turns white. And so after it turns white, the cool thing is we're actually baking the water out of it. And so this chemical right here is cupric sulfate or copper sulfate. It actually has 5 waters in it, and we just baked them out. We actually turned it white. Cool thing is, now that it's white, you can see the white parts. We're about to turn it back to blue. There you go. So once you bake the water out of it, you can actually turn it back to blue by putting the water back in it, which is pretty awesome. And then we'll rinse this off, and we'll do the last but not least. And so this next one is pretty special. This one is lithium, and so this is another ionic compound. This is lithium chloride. So we said that the metal, because it's a different metal, is going to glow a different color. So this one is going to be red, indicating lithium. Let's see. Wow, that's pretty awesome. So the electrons in that metal are jumping up to a higher energy level and then relaxing and releasing a specific color of light. It's called the flame test for metal ions. Right, and awesome. I actually dropped some right there, and it's actually just sitting there producing that red color. Pretty awesome. Okay, and so now we'll be done with that for now. Another thing I wanted to show you is that this covalent compound, compared to the others, so these are pretty hard to melt. These ones should not be as hard to melt. This one actually is a solid at room temperature, which remember we said a lot of covalent stuff is actually a gas already or a liquid already at room temperature. But this at room temperature is actually a solid, and by no means is this a general rule what we're about to do, but I think it's pretty interesting. So we will take this covalent compound, salicylic acid, and we'll put this in the flame, and we'll see, because it's a covalent substance, even though it's a solid, if we're able to melt it. With the other guys, they were on the flame already. You saw that they changed color. They did not really melt at all. We'll see what this one does. It automatically starts kind of sparking a little bit and doesn't really change the flame color all that much. You can see how it's changing it a little bit, but remember the metal below is heating up as well, and then we're actually should be seeing it melt pretty soon. So, and you see maybe a little bit of flashes of red is the contamination from the lithium, but I'm actually starting to see it melt right now, and as it melts it actually reacts with the oxygen that's in the air, like it combusts. You can see the black smoke, the carbon, and so we actually pretty much have a situation where you don't really need a lot of heat and stuff happens. So pretty awesome. Another thing that you could do is take some sugar, and so we have some sugar here. Now sugar, this is sucrose, which is a disaccharide. It's a carbohydrate, and this sucrose is pretty much glucose and fructose, which are simple sugars, combined together to make a disaccharide. And we know that sugar caramelizes at a pretty low temperature, and so it starts doing stuff. It doesn't necessarily melt, really. It just, you'll see, it's going to start browning. You see the brown caramel, and so it starts caramelizing. It's got carbon in it, and so then it will start to turn black. And it's kind of melted there. It looks like a little bit, and so then that one also catches on fire. Sugar is a good fuel, right? Now, carbohydrates are quick energy, and you kind of just saw that there. So pretty awesome when we look at the differences between ionic, metallic, and covalent stuff. We come back to the metal, and I'll show you that, hey, the metal is something that is malleable. It can be bent. It can also be stretched into a wire. So that's an illustration of that. And so really what I'm trying to say is that we have these metallic, ionic, and covalent bonds, and they all have different properties that can be explained by looking at the models that we saw earlier. So hopefully that helps, and we'll see you next time.